So now let's talk about the second kind of more advanced counting technique. And that is really the sum principle. And you remember the sum principle. I have 10 ways of doing this, 5 ways of doing it, and there's this joint, so I can figure out how many total ways. 10 plus 5, 15. Okay. Now, it's easy, right? It's easy to apply, but unfortunately it requires those two things that I counted to be totally disjoint. So what do we do when they're not disjoint? Okay. So in other words, what do we do when I'm counting two sets that actually have something in common, right? So our approach is actually going to follow a pretty simple principle, right? So what I have is that the cardinality of A union B, right, is going to be a little bit less than the cardinality of A plus the cardinality of B. And you can see that in here, okay? So I have the set A, I have the set B, and there's lots of things here. There's lots of things there, okay? And what's happening is when I count the A's plus and I count the B's, I'm counting all these guys in the intersection twice, right? So how to fix this? Well, it's embarrassingly easy, right? We're just going to subtract them, right? Because I counted them twice, so let's subtract them once, and I should have the exact answer. So if I'm adding two sets, right, then the cardinality of A union B is the cardinality of A plus cardinality of B. That's our old sum principle. But now we have to fix. We're going to subtract the cardinality of the intersection. Notice that when A and B are disjoint, then I'm subtracting 0. So this actually does work even in that case. Okay? All right. So let's apply it. I got 50 students in the football team, 75 students in the orchestra, and 12 students in both. So how many students total? Well, that's going to be 50 plus 75 minus 12, right? Because that's A intersect B. Right? So I got 125 minus 12, that's what, 113? Okay, so that should be our answer. Okay, and that's it. I mean, it's as easy as applying it as that. Okay, there's nothing fancy going on. Okay, now let's see if I have 3 sets. Okay, so I now have students. Some of them are cosine majors, some of those are math majors, and some of those are electrical engineering. And but as is very common between these disciplines, because they're pretty close to each other, you're going to find some double majors. So 6 students are cosine math, 4 students are cosine electrical engineering, and 3 students are math and electrical engineering, right? And then we have one overachiever who is a cosine electrical engineering and math major. Okay, now, good for him or her. That's just awesome. But anyway, I still want to know how many students I have total. Okay, so here's what I'll do. I have an overestimate, right? Which is I simply count all the cosine majors, all the math majors, all the ACE majors, and add them together. And I know that's too many, right? So I counted a lot of students more than once. So I now need to take that into account, right? So 6 students I counted twice because they were cosine math. 4 students I counted twice because they were cosine ACE. 3 students I counted twice because they're math and ACE. Okay, so yeah, I need to take one count of those away, right? And so I'll end up with, well, whatever that answer is, right? You know, it's got about 67. Okay, and then what do we have to do? Oops, that cosine ACE math major, right? Because we actually counted that major 3 times. You know, cosine math, cosine ACE, math ACE. So we've taken that major out too many times. Okay, so we actually have to bring it back in. All right, so what we'll do is we'll add 1, right, for the final answer. So that's interesting, right? So you see the pattern, right? And the actual numbers are not important. It's the pattern that's important. First I have an overestimate, then I take out the pairs and now I have an underestimate, and then I have to put in the triples, right? So, you know, in this case I'm done, so that's the final answer. But if I'm not done, then I could have an overestimate again, and then I take it out by taking out the 4s and so on. So that's the idea. That's how we're going to count in these situations. So this is called the inclusion-exclusion principle. So we include some people, so it's an overestimate, and then we exclude some out, and it becomes an underestimate, and so on until we get to the right answer. So here's the plan. I'm going to take the union over n sets, right? And I want to know how many elements are in that union. And so my first step, which is an overestimate, is to say just add up the cardinalities of each set. Okay. Now then after that, I'm going to take out the cardinalities of each pair of sets, right? So what I'm doing is finding the intersection of each pair of sets and taking those out. I'm going, nope, counted out those too many times, okay? But then when I do that, I'm actually taking them out potentially too many times because somebody could have been in 3 sets, so I've taken her out, well, 3 times, right? So let's throw it back in, and I need to consider the intersection of triples. And again, that's great, except I now may have thrown in some people multiple times because they're in actually 4 or 5 sets. So we have to do it again and again and again, and eventually we're going to be maybe taking out, maybe adding, I don't know. It actually depends on the number of sets that I have in the beginning, okay? Because I'm always adding, subtracting, adding, subtracting, adding, subtracting. So when I get to the end, it just depends on whether I had an even number of sets or an odd number of sets. But basically I need to take out or add the intersection of all the sets. And that's the answer, okay? So intuitively, I think this seems like a correct way of counting, okay? Okay, now let's try to prove that. And I'm not going to prove it in a full glory. I'm going to give you kind of an informal argument as to why it's true. So here's the idea. Suppose that X is an element of the union of all, right? So it appears in at least one of the sets. And let's be precise. Let's say that it appears in exactly R of the sets, okay? So what I want to show is that the inclusion-exclusion principle will count X, and it will count X exactly once, right? So if that holds for any X in the union, it's going to hold for all of the X's in the union, so I'm not assuming anything special about X, and that means that each element is counted and is counted exactly once. So that would be our goal. So here's the idea. I said that X is in R of the A sub I, right? So that's kind of R choose 1, right? That's the number of ways that it appears in one of the A sub I. Now, how many combinations of pairs is it going to appear in? And the answer is R choose 2, right? Because I need it to be in A sub I need it to be in A sub j, right? So that means that the I and j have to be 2 of the R sets that contain X, right? Similarly, I want it to be in A sub I, A sub j, and A sub k. That means that A sub I, A sub j, and A sub k, there needs to be 3 of the R sets that contain our elements. So we have R choose 3, right? That's the total number of ways to pick those, right? And so what that means is that we're counting X once here, and then we're subtracting it, R choose 2 times, then we're adding it back in, R choose 3 times, and then we're subtracting or adding it at the end, R choose R times, right? You know, we just go back and forth and back and forth. And this sum, which is exactly the number of ways that I count R over all of the sets, right? I'm just going to call capital N, okay? So capital N is the number of times that I choose R, all right? Now, the rest of the proof actually depends on a couple of really cool facts, okay? We recognize that this is capital N, right? You know, this is just this summation, and it looks an awful lot like a binomial expansion, okay? So in particular, it looks an awful lot like the binomial expansion of minus 1 plus 1 to the R, okay? And remember, right, we did the binomial theorem before. Remember the way the binomial theorem works. If I'm expanding A plus B to the R, then what I have is R choose 0, A to the R, B to the 0, which is this term right here. And then R choose 1, A to the 1, B to the R minus 1, which is this term right here. And then R choose 2, and so on until we get to R choose R, A to the R, B to the R minus R, okay? So that's just the binomial expansion, right, which we talked about last week. And then what we'll have is, well, let's simplify this. You know, R choose 0, that's just 1. 1 to the R, that's just 1. Minus 1 to the 0, that's just 1. So this first term really is just 1, okay? Now the next one, R choose 1, okay, I'm going to leave it like that. Minus 1 to the 1, that's minus. 1 to the R, that's just 1. So this just becomes a minus because of that guy, R choose 1. Now we have minus 1 squared, so that's a plus, okay? That's just 1, R choose 2, and so on. And you can see that is R choose the next highest number with a plus or minus alternating. That's what this sum ends up being. And then we recognize that it's just being 1 minus n, right? Because this whole thing is exactly n. Right? If I pull out well, it's negative n, right? So that's the whole thing is 1 minus n. But now, go back to the beginning. Minus 1 plus 1, That's just 0. 0 to the r is 0. So 0 is equal to 1 minus n. That means that n has to be equal to 1, which is what we wanted to show, right? Because n was the number of times that I was counting x, just an arbitrary element of that union. So the inclusion-exclusion principle really does count each element exactly once, and that's why it works.